right. It is 12 o'clock Eastern, 9 o'clock Pacific in the morning. And so it is time to start our webinar. Welcome, everyone, and thank you for coming today. This is the third webinar in our 6-part series about practical chemometrics in the agriculture sector. Today's webinar is going to be our second part of our building a model, a portion of the webinar series. And today we'll be talking about pre-processing, types of models, and wavelength selection. Before we move on, I want to get through some light housekeeping. Oh, skipped a couple slides there. First, my name is Galen. I am the Director of Applied Science here at Felix Instruments. I've been with the company for 4 years now. My background is in biochemistry and food science, and previously worked in quality and safety testing in the agriculture, food, and cannabis sectors. Also joining us today is Susie Truitt, our distribution manager. She is basically being the admin of the whole meeting, and so she's actually going to be the one in the chat posting any relevant links. She'll also be directing you towards any other resources that we might, as far as questions that you might have that we can't address today. So please, if you are interested in asking a question, do not use the chat function. Please use the Q&A function in Zoom. That way I can see it at the end of the webinar. If you do post a question in the chat, there's a chance I might not see it. We might not get to answering it. If there are any technical issues, if suddenly I disappear or you can't hear me anymore, or the call drops, something like that, please put that in the chat so we can address that before I keep rambling on without anyone actually being able to hear me. So without further ado, let's go ahead and just jump into a little bit of a review. So what we've talked about thus far, and it's been a little while, but what we've talked about thus far in the model building process is sampling and collecting the spectra and performing the analytical testing necessary to actually have the data, build the data sets out to actually then build a model with. So we're at the stage now where we need to start using our multivariate data analysis, our chemometrics, to actually take this data and build it into a predictive model or a discriminant model, depending on what the application is. And so that's what we're going to be discussing today. The next stage is going to be the model deployment. And before we even deploy a model, we also need to validate. So that's what we'll be talking about next in this process. But just a little bit of a review on what we talked about last time. And this is important for today because as much as what we talk about today does matter and has an impact in the quality of the models you build, the most important part, and I think many people would agree with this, the more important part of this process is in the sampling and the testing and this collection of the spectra. Because the saying is garbage in, garbage out. So if you have bad data in your model, you're going to not ever have a really well-performing model. It'll be a bad model. And so really, it's all about having high-quality data going in to the model building process. And then this stage that we're going to talk about today is kind of just a little bit of the icing on the cake. It does have an impact, but it's not nearly as significant of an impact as the quality of the data in the model. So that is definitely the more important step. Today, there is a lot of information. What we're going to do is give you the 30,000-foot view. So just the kind of overview. We're not going to get into the mathematics of all these different techniques. Just going to give you an idea of what's out there, what's been used in the past, what is currently being used, and then we'll talk about some use cases. And then we'll just talk about the practical application of all this information. So multivariate data analysis, or chemometrics coupled with NIR spectroscopy, really has 3 main steps. So we have a spectra pre-processing, wavelength selection step, and then a model selection. So just choosing what kind of actual modeling method we're going to use. And within these three main categories of steps, we also have dozens and dozens of different methodologies that have been developed and utilized in academia and research, in practice. And so we're not going to be able to get to every single one. I'm going to talk about some of the more common ones. I do have some literature that you can, some amazing reviews actually, that you can take a look at yourself in your free time if you want to learn a little bit more in depth about these processes. So first, in this pyramid that you just saw, we're kind of going to build from the first step, which is the spectra pre-processing. Then we're going to build to the next step, which is going to be our wavelength selection. And then our last step, which is choosing which model to use. And so I'll start by talking about a bunch of different pre-treatment or pre-processing methods. And so off the bat, there's going to be you'll see a million different variations of these methods. So even within these methods, there are absolutely different methodologies within these methodologies. And so that's where I'm bringing up, there's just so many out there. It's hard to know what to actually choose or use, but these are just the kind of overarching types of pre-processing. So the first one is spectra smoothing, and this is the most common step that you'll see whenever you're building models. And this is just, as this picture denotes, this is really just taking all of that little bit of extra signal to noise, all that little bit of noise, and smoothing it out so that you're not accidentally creating correlations with something that isn't actually useful information. And so this is usually the first pre-processing step for most models. But like I said, it's almost always just a first step. It's always used in a tandem with another pre-processing or pre-treatment method. Another common pre-treatment method is just to adjust the baseline drift with an offset correction. So if you have a consistent bias in your baseline of your spectra, then it's pretty common just to take that and shift it down so that it's all uniform across all of your data. Similarly to that, sometimes it can be seen that there's an actual linear trend in the baseline drift. So instead of just a constant kind of offset in your drift, you actually have a gradually changing drift. And so for that, they just call it detrending. But really what you're doing is just fitting a least squares trend line to your spectra and then subtracting that from the original spectra so that it kind of centers everything back down to being on the same baseline. Like I said, so these first three that I just mentioned, almost all used in tandem with other methods. So it's just like the initial first step, just to kind of get your spectra in a kind of standardized way, right? There's also like mean centering and other methods similar to this that do similar things, where we're just trying to get all of our spectra onto the same kind of scale and the same baseline, get it all smoothed out before we actually then go and do some of these other methods. So two of the other most common methods that you'll see after you've done these other smoothing or baseline corrections is multiplicative scatter correction, or MSC. This is pretty commonly used in a lot of literature. Really what this method, as well as standard normal variate or SNV, they're both pretty much accomplishing the same thing, just using different methodologies to do it. But really what they're doing is trying to compensate for non-uniform scattering, non-uniform particle size. And so taking that and trying to actually reduce any kind of non-useful information, get it all kind of uniform, all the spectra uniform. And so they just do it using different methods of typically some combination of taking the average of the spectra and dividing that by the standard deviation and then subtracting that from the original, or other kind of variations of that kind of methodology. As far as one other really common addition to the pre-treatment process is the derivatives. So the raw absorbance spectra isn't always necessarily the best type of spectra to use. And so after you've done smoothing, a lot of the times what you'll see are people taking first or second derivatives. This also helps with eliminating drift or scattering, non-uniform scattering as well. So second derivative spectra is a pretty common pre-treatment that you'll see. Some people like to use the raw absorbance as well, but really it just comes down to, in practice, what is going to be most practical for you and what gives you the best performing model. As far as kind of newer and not as well studied or used methods for pre-processing, we have things like wavelet transformation, orthogonal signal correction, and net analyte pre-processing. So all of these things help with very specific kind of problems within your spectral data set. And so wavelet transformation is more a data compression technique. Orthogonal signal correction helps a lot with outlier detection and calibration transfer. And then net analyte pre-processing, that actually is more of a when you have a mixture, but still fairly finite mixture, usually not typically a living kind of or a biological system, usually more of a chemical mixture, and it helps with separating out individual analytes or ingredients within that mixture. So those are more for like very specific things. If you go into an application, where you are trying to build a model and you know that you're trying to accomplish a specific task, like separating ingredients out of a mixture, or you want to deploy a model across a bunch of different types of instruments, a benchtop NIR, a handheld NIR, and a whole bunch of different models, then you're going to want to maybe think about orthogonal signal correction as to help out with that calibration transfer across devices. As far as which are most common and which are used the best, or which are methods just are the best methods to use, it's going to be application specific every single time. And so really you just have to look at your data set and figure out on your own what things you need to do to get that data set as smooth and kind of uniform as possible, while still retaining the important information that you need to get out of that spectra, which is going to be, where things are absorbing in the wavelength range, and being able to see peaks and valleys within your spectra. So it's really going to be up to you to decide that. We'll go into more details about that here later, but I want to get through the actual methods first, and then we'll talk about some practical aspects of this. So the next section or step in the process, right, is wavelength selection. Here, there's a number of different ways to go about it as well. A whole bunch of different methods. You'll see that these are all basically essentially ways of figuring out in the entire wavelength range that my instrument uses, which wavelengths are giving me the most important information. So there's a number of kind of basic ways to do this, and then as the years have gone on, we have more and more complex algorithms to help us determine which wavelengths are going to give us the most valuable information for this model. And so SPA, successive projections algorithm, that's a pretty commonly used algorithm that you'll see in a lot of literature. That one, as well as regression coefficient, which is just the most basic way of determining your wavelength importance, is by just looking at, according to my PLSR model that I just built, which wavelengths are given the highest absolute values in their coefficients. And so that's just like a very basic way of doing it. Loading weights is a very similar to regression coefficient. You're just using the loading weight instead of the absolute value of the coefficient. Then you have stuff like genetic algorithm, which is a iterative process where it's basically starting off with one wavelength and then it's adding on a new wavelength depending on how often that wavelength was utilized in all the other iterations and prioritizes all these wavelengths based on this iterative process that uses a fitness function, which is essentially just saying that anytime the RMSE of cross-validation, which is the root mean square error of cross-validation, is the lowest, then that means that that was a good model. So we're going to keep that wavelength, and then we're going to prioritize a new wavelength and see how well that model gets built, how low that RMSE CV is. And we're going to, so then it just prioritizes wavelengths in that kind of way. Competitive adaptive reweighted sampling, essentially the same as the regression coefficient method. But then you also create subsets from those, essentially from those regression coefficient methods that you used, create subsets of variables, and then you do the same kind of iterative process to figure out which models give you the lowest RMSE CV. Uninformative variables elimination. This is kind of an interesting one. This is actually different than most of the other ones because you're actually adding in variables that are just noise. And then you're building a model, you're building an actual model with those noise variables in it. And then you're seeing which of the actual experimental variables that you have are essentially equivalent to the noise variable, that are equivalent to the noise variables. And so when you can determine which experimental variables are equivalent to those noise variables that you artificially introduced, then you know that those experimental variables have no important information because they're equivalent to the noise that you just added in. And so you can just eliminate those, and then whatever's left is your variables that you want to select. When I say variables, I'm talking about wavelengths. So that's just all kind of interchangeable terminology. And so these are all, all well studied, and they've been used in literature and academic studies. But when it comes down to it, what we're trying to do is with this is select where the most important information is in our wavelength range from our instrument. With the F750, we're looking at mostly in the NIR range, right? We're looking right from 700 to 1200 nanometers. And there's some information there. There's some third overtone information about CH bonds and NH bonds. But really, we're dominated by the OH bond. We're dominated by water. And for the most part, in practice, it is almost always just, it's easier, and it doesn't really change performance that much to just use the entire wavelength range. So that's either called full band, or it's just called not doing wavelength selection. And so when you do full band wavelength selection or no wavelength selection, really you're still getting all the information you need, but now you're just relying on other parts of your model building process, and you're relying heavily on your data collection to make sure that you're not getting all these confounding variables or unimportant signals in your data set that are going to cause your model to perform poorly. And really, this is, in practice, I think what is used most commonly. And so because it's simplicity, because it doesn't require a whole bunch of data scientists in a room to do all this kind of wavelength selection, and it doesn't require rigorous, studying, that it just seems like the most practical way to go about things. And it overall doesn't really affect performance in a very negative way that you might think it would, because all these wavelength selection methods exist. You might think, oh, it's really important to do that, but really it's been shown many times that it's not as significant to the overall performance of the model as you might think. So those are the first two steps, right? We're pre-processing our spectra, and then we're selecting wavelengths. In many cases, we're just selecting the full wavelength range of our instrument. Or just the full wavelength range of the NIR, or just the full wavelength range of the visible light, whatever it is that you're trying to accomplish. And so now we're at the stage where we know we want to do these things. ahead of building the model. And then we want to now select which model type is going to be best for us. So I want to start with discriminant methods because this isn't a super common application as far as the Felix Instruments line of instruments is concerned, but it is an important application in a lot of agricultural sectors when you're trying to do simple things such as detect early bruising, or detect disease, or detect rot, or just even sorting quality into kind of qualitative bins where it's low quality, high quality, medium quality. And so these methods are important to explore because they do have a usefulness with this technology, with NIR spectroscopy. So PCA is kind of the original chemometric method for really what it's used for mostly is reducing the dimensionality of data, and also looking for relationships, looking for these kind of discriminant data sets where in a larger data set, can we see, is there a difference between this type of fruit, this unrotted fruit, and this fruit that is rotted? But really it's mostly used, it's not ever really used on its own as a model building technique. It's more used as a precursor to then performing one of these other methodologies. PLS-DA, which is partial least squares discriminant analysis. This is probably one of the more common types of discriminant methods in the literature. PLS-DA is essentially just a partial least squares regression model, but instead of having analyte quantities as your Y matrix variables, you have just a dummy variable like a 1 or a 0 or something like that. So or a 1, 2, and a 3. It's just a placeholder variable that establishes a class for your different groupings of samples. And so that's essentially how that method works. For some other methods that are also used, maybe not as commonly, but still used, are the SIMCA method, which is soft independent modeling of class analogy. So this one uses PCA, basically a PCA model for each class in a certain training data set. And then each observation is assigned to a class based on the residual distance from the model. And so this is just essentially a slightly more complicated PCA method. LDA, linear discriminant analysis. I would say I see this one and support vector machine are probably second most common to PLS-DA. Linear discriminant analysis is good for both classification and data dimensionality reduction. So just like PCA can reduce data dimensionality, LDA also works really well in that way. Support vector machine is probably on the newer side as far as all these other methods are concerned. But this is a great method for when you have linear and nonlinear data. So if you're basically what you're trying to study doesn't have some sort of linear relationship with the Y matrix, which is the class that you're trying to study, then this is a great method that you can use for that. But discriminant methods are definitely less common, I would say, in what we're trying to do than the actual quantitative calibration methods. And so this is really the more important part of this that I wanted to talk about. So there's been a progression of what kind of models are used the most in commercial agriculture when we're talking, and agricultural research when we're talking about NIR spectroscopy. So it acts as kind of a timeline, really, and also in that way helps guide us into what we kind of should be looking for when we're choosing a methodology. So it started off with multiple linear regression. which is just a very basic linear regression kind of algorithm. But if you have multi-collinearity between your variables, then you're not going to be able to use this methodology. So if you have variables that are similar to one another and they're both increasing at the same rate, and there's, it's a complex system, MLR isn't going to work the best. In general, I would consider most agricultural commodities a complex system. So this is not a technique that I would really recommend anyone be using anymore, because we have advanced so much further than this. The most common, probably, and I believe this is from a recent review published by Kerry Walsh and Nick Anderson, but PLSR, I think, accounts for over 40% of published papers on NIR spectroscopy and commercial agriculture. So PLSR was really used heavily throughout the 90s, because not only because it was the best of the time, but also because it was widely available in a lot of different software packages like MATLAB and Unscrambler and things like that. So these statistical software packages had the ability to run these PLSR models. And so this became a very popular way to go about building models. It's just much easier to just plug your data into a software and then click a button and have it give you output a model. From there, we started to go into the least square support vector machine. This one actually has a decent amount of publications in recent years. This is kind of, I view it as more of a academic kind of situation where I've never really seen this used much outside of academia. So I think it's just, if you have the ability to test it and see how well it performs versus other types of models, sure, it might be nice to try the least square support vector machine. From a practical standpoint, I don't really see the benefit, because around the same time, we also started implementing artificial neural networks. And artificial neural networks are amazing for complex nonlinear systems. So essentially, anything that is a commercially available agricultural product is a complex system, and it's a living biological system. And it's not just 3 chemicals in a pile in a powder form. So it's amazing at being able to generalize across all these different seasonality, regionality, all these kind of issues and variables that we talked about in the last webinar. Artificial neural networks are great at kind of overcoming these obstacles, and they're especially useful when we have these large, diverse data sets. So sure, PLSR might predict really well if you are only looking at one variety of apple grown in a single orchard and you're using a single instrument and you only looked at it in one season. Yeah, that model might be the best possible model you can make. PLSR might outperform everything else. But in practice, if you wanted to then use that model the next season, you're going to run into a lot of difficulties using that, and it will not be an accurate model. However, if you use something like an artificial neural network and you put into practice the things that we talked about last webinar, things like collecting data across different instruments, across multiple seasons, regions, whatever you need, wherever you need the instrument to predict, you collect data from that variable and you include it in your data set. The neural network itself is highly capable of sussing out all these little kind of intricacies within the data and seeing those relationships and being able to compensate for those things. So temperature, changes in temperature, if you just, it'll be able to see that, as there are, there's a relationship here between this spectra changing because of the temperature and the actual Brix value. So we're going to compensate for these changes in the spectra and make sure that they're not over predicting or under predicting during these changes in temperature. So artificial neural networks are really what are being utilized the most right now, typically in a commercial setting. So when all of the Felix Instruments models, we use artificial neural networks, and it's just a great tool for building in all this variability and being able to still get a robust, well-predicting model across all of these variables that present challenges for this technology. Now, that being said, we are now in an era where neural networks have actually been around for a very long time. We just finally started getting around to using them more often in the last 10 years. But now we're in an era where computing power and computing algorithms are increasing exponentially every day. And we're finding that there's newer and newer deep learning techniques that could be even more beneficial to this technology than the kind of baseline artificial neural network. So there are other artificial neural network architectures that are deep learning techniques that we can start to explore to actually see whether or not we can get even better performance with the benefits of having to do, shorter training times when you're actually building the model, parameter reduction, downsampling. So basically reducing all the computing load of these models, but still getting the exact same performance, which would mean we could build, whereas right now it might take us for a 10,000 sample set model, it might take us 4 to 6 hours to build a model, to train a model. Now it might only take us an hour to train a model. And so that allows us to run even more iterations, explore more options to ensure that this model is the best performing model we can possibly put out. So this is an avenue that we're going to be starting to explore, the convolutional neural network. Essentially, like I said, it's just a different type of artificial neural network architecture that it's doing slightly different things than a typical neural network is. But it's really exciting, and there are even more deep learning techniques that are available that we can start to explore now that we have the resources to do so. We have all these cloud-based servers that have all this information already built into them, and we can just start exploring and seeing how well these models can perform with the convolutional neural network, with other types of deep learning structures. So before I get into any formal recommendations for this kind of, this whole process of choosing spectra preprocessing and wavelength selection and model types, let's first just look at 2 use cases, and so I can kind of use those to help you understand how to choose between all these different methodologies, essentially. So our first use case is going to be a Chinese farmer that grows a single variety of jujube from a single orchard, wants to build a model to non-destructively predict their soluble solids content. So this is a quantitative predictive model, and they only want to deploy it on a single instrument, a single F750. So they explored multiple different types of wavelength selection methods. They decided to utilize the multiplicative scatter method of spectral preprocessing. And then for their calibration methods, they wanted to look at both PLSR and the LS-SVM. So looking at every permutation of this combination or of these various methods, they tried every single permutation and just examine their results to see which one is going to give them the best results. So looking at the methodology. So they always used MSC for their pre-processing, but looking at the one where they did no wavelength selection or a full band selection, essentially, and they just used MSC for pre-process and they used a PLSR calibration method, that actually gave them the best performance. You know, it's another one of those things where you can try, you know, you can put a lot of work in and use all these different types of methods, but it could turn out that the easiest and most practical one is actually the best performing one. And we see that actually a decent amount. For instance, they're using here the MSC, and then they used a stepwise regression analysis, which is another wavelength selection method. And then they used PLSR. That gave them a 0.06 reduction in their R squared and increased their error by 0.3. And for soluble solids, that might be, you know, 1.3, 1.4 might be too high of an error, average error to use in practice. For the MSC SPA, the projections algorithm, and then using the LS SVM calibration method, gave them an even worse R squared, but the RMSC went down slightly. So it was just in between the two methods. Now, this is where I want you to see the kind of the bigger picture. When I said at the beginning, the sampling is the most important part, and that this is more like the icing on the cake, the, you know, just something you can experiment with, but isn't going to determine the overall quality of the model nearly as much as the sampling and the testing. Here's where you can see that evidence. We're talking about differences in the hundreds for most of these statistics. And, you know, this is a lot of work. This is a lot of work to go through all of these different wavelength selection methods and pre-processing methods and calibration methods. They're, you know, they're changing all these things around. They're trying every single permutation, but in the end, it's only changing the model just slightly, you know, very, very slightly. So it's really, you know, it's important to understand that in practice, like this is, it's fine if you're a researcher and you're doing something and you want to cover all your bases. You want to actually evaluate the performance. That's, you know, part of what you actually want to look at is all these different types of methodologies. That's great. And you can absolutely do that. But for everyone else that's actually wanting to use these in practice in their commercial operations, this is maybe not the most practical way to go about doing things. And simplicity is oftentimes just as good as far as selecting these methods. Simplicity is just as good as going through and doing the super exhausting work of checking out every single possible permutation of and combination of these methods. So let's look at another use case. This use case is in Australia, and we have a network of Australian mango growers with dozens of orchards, dozens and dozens of orchards spread out across various regions across the entire country. And they want to create a model that will non-destructively predict dry matter and bricks in several different mango varieties, 4 to 6 different mango varieties. And they want to be able to deploy this singular model on over 30 different devices. And they want those devices to be going out to all these different regions and taking measurements, and they want them all predicting fairly similarly. So what we've done, or what they've done, is do Savitzky-Golay smoothing and then Savitzky-Golay second derivative. And so what we've done is smoothed out the spectra, gotten the second derivative of that spectra, and then it's time to choose the wavelength. And they're really just going full band, essentially full band NIR. So not really selecting any particular wavelengths, not performing any algorithms or methods to select specific wavelengths. And then for the calibration method, using a neural network and collecting good data from all these different regions, from all these different varieties across multiple different instruments, calibrating them using the neural network, they're getting an RMSEP of on average less than 1. So this is an RMSEP, which is on an independent validation set. So that's showing robustness. That's showing this model can predict outside of its own training data sets. And that's the actual practical use of the instrument. You're never using the instrument on the same exact data you use to, or same exact fruit you use to build the model with. So the RMSEP is a very important statistic, which we'll talk about in the next webinar series. But the point here is pretty, straightforward, simplistic methodology to get this model built, and really good performance because they really did their due diligence to collect really good data. And so that's where I think the practicality discussion comes in. Is there are, as I mentioned, dozens and dozens and dozens of different methodologies you can put into place to try to build the best possible model. However, when you want a model that you actually want to use in your, in your industry, in practice, you want it to just work season to season. You want it to work, across different orchards or across multiple instruments. Say you're if you're a pack house, you're getting in 16 different varieties of apples in your pack house, and you need it to be able to work across all your different varieties of apples. This is, I think, the best advice I could give is to start simple. And if you can't get good performance or reasonable performance out of your simple model, and simple being smooth your, always smooth your spectra. I don't think anyone shouldn't be smoothing their spectra. Always smooth your spectra. Do a derivative if you want, or some other kind of other, more simple correction of the spectral in the spectral preprocessing. Do a full band, or no wavelength selection. Just do your full NIR region that you have available to you, and then use a neural network. See what happens. See what kind of performance you can get. If you are incapable of getting a model that is even somewhat reasonable, the first thing I would do is go back and look at your data. I would go back and look at how you collected your data, and I would look at the data itself before you start going and exploring a whole bunch of different options for all these methodologies. That's where it all stems from. Now, as for, and the other part of that is not everyone has data scientists on their hands. I myself am not a data scientist. And so there is also the gap of like, what can you actually do? And so there are tools out there, you can use R if you know someone that can use R or RStudio to do these model building exercises. You can use Python. That's what a lot of data scientists use, and TensorFlow, or you can use, if you're using a Felix Instruments, you can use our software app builder, which is just the same idea and concept as what Unscrambler or MATLAB was, but this is specifically for our instruments, and it's specifically meant to help you build neural network models without having to do any of the actual complex, data science behind them. So, there's tools out there that you can use to do this. And because not everyone has data scientists on hand, it might be useful to start simplistic, and then, maybe later think about, after you've already examined your data, think about using other methodologies. But, and that's in practice. Obviously, in academia, it's going to be a different story. But that's my advice to all of you as far as this step of the model building process is concerned. As I mentioned, there are a couple of reviews out there that are really good if you want to read more about all this kind of technology and on the methodologies used for the actual model building, the chemometrics side of things. So Nick Anderson and Carrie Walsh have a 2022 review, the second part of which should be coming out soon, should be available soon. but this is the first part of that review, and has a lot of good information. And there's another review by Wang et al. That goes over a lot of what I talked about as far as the pre-processing and model building techniques. So those I would highly recommend reading and further into those if you are more interested in learning more about what I was talking about today. So just to kind of give you a sneak peek for the next webinar we're going to do, this first section of our three-part series, the model building section, is actually now completed. So if you want to, this webinar will be recorded and sent out for anyone that registered, but we also put our webinars up on our YouTube. And so if you need to access the previous parts, if you weren't here for the sampling, part 2 for the sampling and the analytical testing best practices section, you might want to check that out and review that. What we're going to go ahead and do in the next webinar series is actually go into our model validation. And so this is a often overlooked step in this entire process. And so this is going to be a lot of good information about how to perform validation testing and what relevant statistics you should be using to determine whether or not this model is robust and whether it's actually going to be able to predict well for you outside of the the kind of bubble of your training set data. And so we'll kind of challenge you to get out of that mindset of only looking at your training set, but looking at independent validation and things of that nature. So that will be the next part of the series. And then we'll go into a little bit about the challenges in calibration transfer. And then our last part of the series will be about how to maintain your model and optimize it after you've deployed it. And so then, that'll be the end of our chemometrics series. But thank you so much, everyone, for joining us today. And I hope you've learned a good amount. And I hope that you have the confidence to kind of go into this process if you are thinking about it. Confidence to go in and make some decisions now about what you should be doing and looking for when you go to build your model. So if you are interested, Susie will put a link to the quote for our devices. That'll be in the chat function. So if you go into the chat, you'll see a link there. If you're interested, you can request a quote for pricing. Also, if you want additional information about our F750 or F751 or any other of our products, or just if you want to stay updated on our projects, we also have great newsletters and emails that we send out with really great information about current studies that are happening, current things that are new research in the fields. And so you can follow us on any of our social medias or go to our website to find all that information, sign up for the newsletter. Thank you all so much. So what we'll do now is go into the question and answer function here, and I will actually answer as many questions as I can get to. We have limited time, so I'll get to as many questions as I can. If I don't get to your question, don't be concerned. We will make sure that we answer your question via email. Okay, so first question is, does CID Bio facilitate with publication of original research articles in an impact factor journal? I think what you're asking is, do we work with researchers to help collect data or do things to help get them published? And if that's the question, then we like to collaborate with researchers all the time. Whether or not that's for publication or not is typically up to whether or not the research they're doing is something that the researcher is interested in publishing. Depends on the project. So if you want to reach out to me individually to discuss your specific case more, then feel free to. Susie will put my email in the chat if you want to reach out to me about that. So the next question from Georgie is, what about COM-DIM regression? So as I mentioned, I am not a data scientist and I don't claim to know every single type of regression analysis that's out there. And so there very well may be many others. I do not know what COMDIM regression is personally. So I have never seen it in a publication in commercial agriculture specifically. You know, if it's a novel model approach, then that is actually a good starting point for a new publication, I would say. So that's my response for you, Georgie. The next question, how many spectra will we need to build a sturdy machine learning model? This is the most commonly asked question when people ask us about building models, is how many spectra, how many samples do I need to build a good model? And there is no answer for that. There is no way we can just say, give you a number and have that be even close to what might be needed. In general, it's, you know, it's going to require data. I mean, it really is application specific, but in the use case of, I need this model to work over multiple seasons on a single instrument for a single commodity, single variety of a single commodity in a single region, then at the very minimum, you're going to need more than one season's worth of data in that model. And so, you know, that's if all your other variables hold constant as well. So it's not about data quantity as much as it is about representation. It's making sure you are representing all the variables that are present within your data set. So regionality, seasonality, temperature, a variety of commodity, all those things need to be evenly represented within your data set in order for it to be a well-predicting, robust model. And it's not so much about quantity, but if there's that many variables present, you know, there's going to be more data than less in general. So that's really the best I can to respond to that question. But it's a valid question that, you know, I wish there was an answer to, but really it is pretty much an application specific kind of question. The next question from Endreet is, does the F750 come with sample models, or can we get them somewhere in order to familiarize? Yes. So not just, pardon me, not just sample models. The 750 actually comes with 3 robust models. So we have models for avocado, mango, and kiwi fruit at the moment. We also are hoping to have our melon model finalized here soon. And so the F750 comes with all 3 of those models, as well as some sample models that are more proof of concept. They aren't robust models. They were just developed to demonstrate that the device is capable of measuring these things in certain commodities. So we do have some of those models as well, but the device comes with 3 robust models that use neural network chemometrics. And so that'll help, and that can help you get familiarized with the device itself and those kinds of predictions that you can get from neural network chemometrics. And the last question here is, make sure we send an email for the next event, as I found it excellent opportunity. If physical workshop is managed, that would be of great value. Excellent. I'm so glad that you gained some knowledge from this. That's all we really want, is to make sure that people are being given the information that they should be when it comes to this technology. And we absolutely will make sure that everyone that was attending today will be on the mailing list for the next section of this webinar series. And yeah, if we ever do another physical workshop sometime, we will make sure to let you know. But yeah, and that's the last question on this list for now. Again, if you have one that comes up later in your mind, or if you had one that you forgot to put in the question and answer section, please feel free to just drop that via email to us, and we can answer it over email. But again, thank you all for joining. I hope you learned a little bit about this, seemingly complex and rightfully so, kind of process of model building, but it's not as scary as it might seem or complex as it might seem. It's all very manageable. And so I hope that we can instill that even more in the following webinars that we do for the series. But till then, thank you all so much again, and I hope you have a great rest of your day.